Hi, everyone. Okay, last lecture we saw that, or last video, I should say, we saw that the curvature, which I'll write as kappa, is defined as the derivative of the unit tangent vector with respect to the arc length parameter. Okay, so in this video, he uses double bars. Many people do. Single bar is also unambiguous when you're talking about vectors. So either notation we can use interchangeably. We can keep track of both of them as just meaning the length of a vector. Okay. And remember what t was in terms of our parameterization variable, little t. So capital T meant the unit tangent vector. And this is a vector, by the way. So r prime, this was the unit tangent vector. So this is r prime divided by the length of r prime. Okay, so that's a unit tangent vector. So let's try to find a formula for the curvature in terms of, let's try to find a formula for the curvature in terms of the parameter little t. So this is the definition of the curvature. Okay. All right, so by the chain rule, we know that d capital T, d little t, is d capital T, d little s times d little s dt. Okay, that's just a chain rule from uh, ordinary calculus. Okay, and so we know that kappa, which is the curvature, that is the length of the vector dt ds, is then equal to, so dt ds is d capital T, d little t in length, because I have to use this line above, but then take lengths of these vectors, divided by the quantity d, the length, or the absolute value of ds dt. Okay. But what is the length of ds dt? That is exactly the length of the vector r prime of t. We saw that when we defined, by using the fundamental theorem of calculus, when we defined the arc length function. So that denominator is just the length of r prime of t, and this we can use the notation d capital T, d capital T, but here I mean a derivative where I'm expressing the unit tangent vector in terms of the parameter t. Okay, so what we just showed is that here's an alternate version of the definition of curvature. Okay, sometimes this definition is more convenient than the one up top. It just depends on the exact problem you're given and what the ingredients of the problem are. Okay, so now using this formula, it's easy to get a nice little lemma, you could call it, or a little proposition, which we'll call an example here. The curvature of a circle of radius A is 1 over A. So the curvature of a circle of radius A is 1 over the radius. So if you think about that, what that says is that small circles have big curvature and big circles have small curvature. So in our heuristic definition of how fast a curve bends or how steeply a curve bends, if you have a very small radius A, then 1 over A is really big. It means it's bending very steeply. And conversely, if A is really big, then 1 over A is really small. That means it's bending very gradually, very slowly. Okay, so let's show why this is true. Okay, so here's the little proof. How do you parameterize a circle? The most convenient and most standard way is to parameterize it by going cosine t, and let's make it a circle of radius a. So we'll say a cosine t I plus a sine t j, and we will let t go between 0 and 2 pi. So that parameterizes a circle. Okay, that's very well known. You should be familiar with that. Okay, so in order to compute our curvature, we need, here's our R parameterization, which we sort of have to know the parameterizations that are common. And we need to figure out R prime. Then we'll need our unit vector, capital T. Then we'll need to differentiate that. Then take a bunch of lengths. Well, not a bunch, two. Okay, so let's think about doing that then. Okay, so what is R prime of T? So here's my formula for R. So my R prime is going to be minus a sine T I plus a cosine T J. Okay. And now and now, so that's, we can do the length while we're at it. So R prime of T, the length of that vector is the square root of a squared sine squared plus a squared cosine squared. So you factor out a common factor of a squared. So this is the square root of a squared times sine squared plus cosine squared. Sine squared plus cosine squared is 1. So this just becomes a. So the length of the vector r prime of t is just a. And now how do we get capital T of t? You can't find capital T prime till we first find capital T. So capital T of t is r prime of t divided by the length of r prime of t. Okay. All right, so let's see. That is when I take the length of r prime of t is just a. So take my formula for r and divide each component by a. I will get the vector cosine ti plus sine tj. So that's taking the vector r prime. I'm sorry, copied it wrong. This becomes, let's do it correctly. I have to take r prime and divide by the length of r prime. So it's this one divided by a. So this becomes minus sine ti plus cosine tj. Okay, so that's capital T. And now we need capital T prime because that's the one we're going to need the length of. So now differentiate this. This will be minus cosine ti minus sine tj. Okay. And now let's compute the length of that vector. So the length of capital T prime of t is going to be the square root of cosine squared t plus sine squared t, which is just the square root of 1, so it's just 1. Okay, so therefore kappa, which is, if you remember, a second definition of the curvature was the length of t prime, little t, divided by the length of r prime of t. The length of t prime of t was 1. The length of r prime of t was a. Therefore, the curvature is 1 over a. And that's what we claimed it was. Okay? All right. So big circles have big curvature. Big circles have small curvature. And small circles have big curvature. Okay, one last thing I'd like to show you, a third formula for the curvature, call it a theorem, is the following. That kappa is r prime cross r double prime, the length of that vector, divided by the length of r prime cubed. Okay, That seems a little unbelievable and a little unusual. So let's see why that's true. And it'll give us some good practice with reviewing the unit tangent vector and its relation to the arc length and all that sort of thing. And the good practice with the chain rule and differentiating. Okay, so remember that capital T is r prime divided by the length of r prime. That's functions of t, okay? So that tells me that little r prime I can write as the length of r prime times capital T. But if you remember, the length of r prime of t is the derivative of the arc length function with respect to t. So here's another way you can write r prime, okay? So now let's take this formula, and I'm going to differentiate with respect to t. So that I get r double prime, okay? So when I do that, I have to be careful. R double prime of t is going to be, now it's a product rule, so that will be the derivative with respect to ds dt, you differentiate with respect to t, so that'll be d squared s dt squared times t plus the first times the derivative of the second, which will be capital T prime. Okay? All right, and now we want to take, we, we want to look at capital R prime, little r prime cross little r double prime. Okay? So that is little r is ds dt times capital T, and little r double prime is this sum. So that's the second derivative with respect to t of s times t plus ds dt times capital T prime. Okay, so now that's the cross product, but you have a sum over here. So you have to be very careful with cross products. So this is ds dt times the second derivative of s with respect to t. And then I have vector t cross vector t. Okay, but a vector, when you cross it with itself, is zero. That's one of those properties of cross products. So this one goes away. But we still have to take this guy cross product with this term and say plus here. Okay, so here we will have ds dt quantity squared times t cross t prime. Okay? But we know that t is a unit vector. So by our previous example that I did in an earlier video, t is orthogonal to t prime. We showed that if a vector has constant length, then the vector is orthogonal to its tangent vector. And this is the unit tangent vector, and its tangent vector must be orthogonal to it. Okay? In other words, the angle between capital T and capital T prime is pi over 2. Okay? Okay, so if we go to look at the length of r prime cross the length of r double prime, because that's what appeared in the formula, so that's what I'm going to look at. So now I go to this vector and I start taking lengths. Well, this first one's 0, so that doesn't come in. Here, this is already a square, so we have ds dt quantity squared. That's positive, so it's good. And now the other term will be the length of t cross t prime. But what is a formula for the length of the cross product of two vectors? That is, by what we learned in an earlier section, it's the length of one times the length of the other times the sine of the angle between the two. But the sine of pi over 2 is 1. So this is equal to, well, it says that, let me say it this way, that the length of capital T prime, because this is 1, is equal to, whoops, another thing we know is 1 is the length of T, because T, that's a unit tangent vector, so that's 1. So we have that the length of T prime is equal to the length of R prime cross R double prime divided by ds dt quantity squared. Okay. But what is ds dt quantity squared? ds dt is the length of R prime of t. So this is the length of R prime cross R double prime divided by the length of R prime squared. Okay, so we have this formula for the length of T prime. And now we put that back into our formula for cap, which we derived earlier, that the curvature is the length of T prime divided by the length of R prime. So kappa is the length of T prime divided by the length of R prime, but the length of T prime is the length of R prime cross R double prime divided by R prime squared, but we have another length of R prime, so this becomes the length of R prime cubed, which is the theorem we advertised, okay? And sometimes that's a more convenient way. This theorem may be a more convenient way to compute the curvature. It just depends on the problem you're given and what you've done beforehand, so whether or not you're set up to do this formula or one of the other ones. Okay, so now you should head over to the WebAssign and work on the problems for this section. See you later.